Ma'am, you can start now.
I can start? Okay.
No, Tima.
Yeah.
Okay, sir. Good evening to one and all attending the session. I'm Hemalata B, IEEE Student Secretary of Photonics Society from the Department of Electronics and Communication Engineering, St. Joseph's Institute of Technology. I'm here to volunteer for today's session. On behalf of EC Department, St. Joseph's.
Whoops. I lost the sound.
1 second, ma'am.
A hearty welcome to Dr. Carmen Menoni, University Distinguished Professor at Colorado State University, USA. I would like to mention our beloved Chairman, Dr. B. Babu Manoharan Sir, and our Managing Director, Mrs. B. Jesipriya Ma'am, and Director, Mr. B. Sasishekar Sir, and our Principal, Dr. P. Ravichandran Sir, for giving this wonderful opportunity to conduct this webinar. And special mention to our department heads, Dr. C. Jnana Kausalya Ma'am, Professor and Head, Staff and Student Affairs, and Dr. G. Rohini Ma'am, Professor and Lab Affairs, for their guidance and constant support. Now, I'll be sharing a few words about the speaker. Dr. Carmen Menoni is University Distinguished Professor in the Department of Electrical and Computer Engineering. Professor Menoni's expertise is in optical and material science. Her research focuses on the development of novel interference coating architectures for power scaling of mid-infrared lasers. Her research in optical coatings is tailored to solve critical issues of laser damage in light sources with unique pulse structures. Part of these efforts are also devoted to investigate pathways to realize ultra-stable interference coatings for gravitational wave interferometers. Professor Menoni is also involved in using high brightness coherent beams of light of wavelengths between 10 to 50 nanometer for optics applications such as nanoscale imaging, ablation, and chemical imaging. Professor Menoni is a fellow of IEEE, OSA, APS, AAAS, and SPIE. Professor Menoni is the president of the IEEE Photonics Society. Thank you, ma'am, for joining us today. Before we start the session, yes, ma'am, thank you, ma'am. Before we start the session, I would like to tell a few instructions to be followed by the participants. Kindly post your queries and questions in the chat box, and they will be discussed with the speaker at the end of the session. The attendance link will be posted at the end of today's webinar. Now, I invite our speaker of the day to kindly start the session. Ma'am, the screen is yours.
Thank you very much, Hemalata, for this kind introduction. It's a pleasure to be talking to you about, the work that I am doing with my students in research, and also about, the IEEE Photonics Society. So this is what this talk is going to be about. First, I will talk about materials that we use to make interference coatings, which are photonics structures. They are the equivalent to they are equivalent to transmission lines in the optical regime, and also, they are photonics, very important photonic structure for many applications. And then the second part of this talk will actually cover some background on the Photonics Society and the efforts of the Photonics Society, in particular for the mentoring of students like you. So, okay. So we develop thin film metal oxides, and these materials are very broadly used in photonics technology. One example is shown here, where we have a grating coupler that was fabricated in tantalum pentoxide for nanophotonic circuits. Now, this is a schematic of the device. And what you see here is that we have essentially like a diffraction grating. We have a periodic pattern of the tantalum pentoxide. And because tantalum pentoxide has a refractive index at 1 micron of about 2.2, then having air and then the material offers a large index contrast that allows for guiding of the light. Similarly, what you see here is an example of an ultra-low loss tantala waveguide. That's the core, and then is cladded by SiO2. And so this the index difference between the SiO2 and the tantalum pentoxide is what gives you the conditions to be able to guide light. So what is unique about these materials is that they can be deposited by physical vapor deposition, and they can be made in the form of very thin layers. And that's what I am going to show you. So our application is in the development of interference coatings for near-infrared lasers and high-finesse optical cavities. And what you see here are the structures, the devices that we grow. And they consist of stacks of layers of two materials that have a contrasting refractive index at the wavelength of interest. In this particular case, I'm using hafnium dioxide and silicon dioxide. Then we layer them in a specific sequence. We do this all with software that is available. And then we can tailor the optical response. And what you see here is a transmission electron micrograph of a real coating structure made out